In this video, we'll cover the essentials of Gigabit Ethernet hardware design. We'll start by looking at the components involved, such as MAC, physical layer, magnetics, and connector, see how these are connected together, what interfacing standards we will be using, what signaling, for example RGMII, MDIO, and so on, how we might be selecting certain components, and what these components look like in detail. In particular, the physical layer, what signals need to go to and from this device, how this is configured, what power supplies it needs, clocking, and so on. We'll also be looking at a real-world board, the board you are seeing here, which incorporates an AMD Xilinx Zinc system on chip, which integrates a Gigabit Ethernet MAC, which on this board interfaces with the Realtek Gigabit Ethernet PHY or physical layer connected via RGMII. Then the PHY connects to a MagJack Ethernet connector. We will be following this board along, looking also at the schematics, how everything is linked up and tied up, what we need to pay attention to, for example, strapping options, decoupling, and so on. And finally, we will be looking at the PCB design, looking at layout and routing, what we need to pay attention to, for instance, controlled impedance, delay matching, and general PCB design best practices when you are incorporating Gigabit Ethernet into your own PCB designs. If you're interested in seeing these designs in action, I do have a video on my channel, which is part of a series of FPGA system-on-chip bring-up showing a custom board using the Xilinx Zinc chip. For example, video number 99 on my channel shows this particular physical layer and this particular Zinc system-on-chip running Gigabit Ethernet very close to the 1 gigabit per second speeds, as is demonstrated in that video. So if you'd like to see that action, please check out the link in the description box below. Although we will be covering quite a lot of ground in this video, of course this is condensed, there are many other resources that go into more detail on certain topics of Gigabit Ethernet or Ethernet in general, which I strongly suggest you check out if you're interested. I will leave several links in the description box below as usual. For example, this video by Viet Electronics, Design Essentials for Gigabit Ethernet Frontends, for example. A huge thank you to PCBWay for sponsoring this video. I had these AMD Xilinx Zinc-based PCBs manufactured and assembled by PCBWay in China, and they did an absolutely fantastic job. For this, I used their advanced manufacturing service. This is because this is a fairly complicated design with fairly small drill hole vias. I needed controlled impedance, and this overall is an 8-layer board, as we'll see. The advanced PCB service can cater to all of these designs up to 60 layers, down to 3mm track spacing. If you want, of course, HDI with buried blind and micro vias, and many different custom options, which I made use of also for this particular design. Many thanks also to Altium for sponsoring this video. We'll be looking through the schematic and PCB design in Altium Designer, but of course the tips in this video are tool agnostic. If you would like to give Altium Design a try for yourself, including all the cool Altium 365 features, such as advanced library management, data management and version control, supply chain management, and much more, make sure to check out the link in the description box below at altium.com/YT/Phil's Lab to get yourself an Altium Designer free trial, as well as 25% off your first license purchase. To start off, let's look at a very high-level overview of a typical Gigabit Ethernet implementation, and then we'll hone in from there. There are typically two methods of doing this, and there's one at the top, one at the bottom. But in essence, they are the same thing, just split up slightly differently. Starting on the top left-hand side, I have an SoC, which is a system on chip, which is what I'm using in my case, which is this AMD Xilinx Zinc. Essentially half an FPGA and half an ARM processor. Now, of course, it doesn't have to be a system on chip. It could be a processor, or it could even be a microcontroller. Many microcontrollers these days integrate Ethernet MACs, oftentimes 10 or 100 megabits per second, but I've seen some processors or microcontrollers that integrate now Gigabit Ethernet MACs. So the MAC is typically contained in your processor. That MAC interfaces digitally with an external PHY or physical layer. This PHY is effectively a transceiver between the digital and analog world. So on the left-hand side, we have our processor. On the right-hand side, we have our interface, very simply speaking, via connected to the outside world via your typical Ethernet cable. We have two different sets of interfaces on the left-hand side, and we have one interface on the right-hand side. On the left-hand side, we typically for Gigabit Ethernet have a media independent interface, or MII for short, and for Gigabit Ethernet, that's GMII, Gigabit. The media independent interface for Gigabit Ethernet is 8 bits wide per receive and one 8-bit wide bus for transmit line plus some other signals. Therefore, oftentimes we will find an RGMII, which is reduced Gigabit media independent interface, which cuts that bus width down to 4 bits. This RGMII interface is mainly for data transfer. This is our high-speed data transfer, but to actually configure the Ethernet physical layer, for example, to set auto negotiation, to set maybe what the LEDs do, we will need another configuration interface, and this is MDIO, and this is management data interface. And you can think of that very similarly as I2C or SM bus, with a unidirectional clock line where the MAC drives the PHY, and we have a bidirectional data line for transfer of control data between our MAC and our physical layer. On the right-hand side then, we are effectively in the analog world. The physical layer drives the differential pairs that then feed, simply speaking, the Ethernet cable. Between the PHY and any connector, we will need some form of magnetics, and these are transformers. These are for isolation. Many times you might find the magnetics are a separate part on the PCB, and then we have a separate RJ45 connector. But oftentimes, and what my preferred method is, unless you have very specific isolation requirements or requirements otherwise, is that you simply from the Gigabit Ethernet PHY, we have our MDI connections straight into an RJ45 connector with integrated magnetics. And these connectors are typically called MagJack connectors. For us on a board and hardware level, what we really need to be concerned about is the choice of processor, the choice of physical layer, and in our case, we'll actually go with the bottom option where we'll be choosing an RJ45 connector with integrated magnetics. So we need to familiarize ourselves with this MDIO signaling, with the RGMII signaling for the data transfer, as well as the MDI signaling and the parts in between. As we'll just skim over this in this video for the sake of time, make sure to check out this Wikipedia article on the media independent interface, this MII interface. This talks about reduced media independent interface, gigabit media independent interface, and what we'll be using in our video, this reduced gigabit media independent interface. For the RGMII, we can see the supported Ethernet speeds, so up to 1 gigabit per second, how many bits per clock cycle we have, and the core clock frequency. In terms of signaling, and we'll see this on the schematic later as well, these are our main RGMII signals. We have one grouping for transmission from the MAC to the PHY, and one group of transmission from the PHY to the MAC. We have a single line for the clock signal, a 4-bit wide data bus, as well as its control signal. And these same sets of signals we have for TX and for RX. Separately, we then have these MDC and MDIO signals. Again, this is very similar to I2C, where we have a unidirectional clock and a bidirectional data bus. And again, the clock is driven by the MAC sent to the PHY. There are, of course, various signaling standards that these interfaces have to adhere to, and we'll see a tiny bit of that later on. In terms of actual integration on the PCB, here's a real picture of the PCB, just a snippet of the relevant section for this video. So we have the AMD Xilinx Zinc on the left-hand side, which is half FPGA, half ARM, very simply speaking, and contains a Gigabit Ethernet MAC, I believe even 2 of them. So this will have interfaces with RGMI signals and the MDIO signals that need to be routed to the Gigabit Ethernet PHY, which we can see on the right-hand side here. So RGMII still is a rather wide interface that we have to route fairly carefully, impedance control, delay match, but we'll get to that later on. And from that physical layer, we then route with 4 differential pairs to and from this RJ45 connector with integrated magnetics. The reason I chose an RJ45 connector with integrated magnetics, MagJack for short, is that it makes the routing far simpler, and it saves onboard real estate, because rather than needing external magnetics between the physical layer and this RJ45 connector, the magnetics are integrated into this connector. So the routing, as we'll see later on, is very simple indeed. The most difficult or time-consuming part of the routing is between the MAC and the physical layer, and in particular the RGMII interface. There are some components we can see around the physical layer, and we'll go into more depth. You can see there's quite a few resistors. As we'll see later, a lot of them are series termination resistors and strapping resistors, as well as decoupling, which is actually on the bottom side of this board, and we have separate clocking requirements. The next question is, if you're designing a hardware system, assuming you've got a suitable processor chosen, what physical layer IC do you choose? And there are quite a few parts you can actually choose from. So let's go to a typical distributor and check some of these parts out. Looking at a typical distributor, for example, Mouser in this case, and then going to semiconductors and Ethernet ICs, we can begin our search, or at least compare what different options we have for the various physical layers. Just looking at the suggested filters from Mouser, scrolling a bit to the right-hand side, we can see what Ethernet standards we might be looking at, what data rates, what interface types we have, supply voltage, max and mins, operating temperatures, and so on. In our particular case, we want a Gigabit Ethernet PHY, and typically PHYs that are capable, for example, of a gigabit per second are often downward compatible to 100 megabits per second and 10 megabits per second. So we might choose some suitable options that go up to 1 gigabit per second. If I click on in stock and just click apply with these very basic filters, we can see we still have 182 results left. There are other options, for example, number of transceivers, interface types, package types, and so on. Oftentimes, Ethernet PHYs will come in QFN style packages, but can of course come BGAs or even QFP style packages. From what I've seen, the most common ones are in QFN style packages. In terms of interface type, we do want RGMII because you want the reduced gigabit media independent interface. So we could, for example, select those interface types to narrow the search down further. You will of course have to choose your Ethernet PHY based on the required standard you're using as well. We will be going with 1G base -T. But if we just leave these filtered as they are for now, and I've just sorted by price, we can still see where there's quite a few parts remaining. And this choice can oftentimes seem overwhelming. Of course, as usual, you should choose your parts based on availability, long-term availability, manufacturer lifestyle status, cost, package type, and of course the features that you require in the physical layer. For simple, non-demanding applications, let's call them, which might be your everyday use case, unless you have very specific requirements, most of these physical layers will do, but do choose them depending on your requirements. In terms of compatibility, for example, for setting up the control registers of these physical layers, the basic set of control registers is actually standardized by the IEEE, so most PHYs should be compatible with whatever Mac you're using. However, there are of course exceptions, and you should definitely check that there is compatibility between your Mac and your chosen PHY or physical layer. I'd strongly suggest choosing a physical layer that's been proven to work with your Mac, and there might be already existing drivers or configuration for the PHY and Mac combination of your choice. The particular AMD Xilinx Zinc IC I happen to be using is an XCZ20 variant in a specific package type, and for that there are many different development boards and eval boards already available. So before designing this boards and other boards, I would typically check out maybe an evaluation board, a development kit, and see what physical layer, for example, the manufacturer of the particular processor has used in the design in terms of PHY and external componentry. So you might be looking at something from a third-party vendor or AMD Xilinx themselves or whatever processor manufacturer you're going with. I happen to be quite a big fan of the Digiland boards, and they, along with quite good documentation, also provide the schematics for most of their designs. For example, if we go to their system board section on their website, looking at the Zinc 7000 series, for example, a Core Z7 or an RT-Z7, if I open this link, scroll down and go to support, and then click on schematic, we can have a look through what they used for their Ethernet physical layer. And lo and behold, they've used an RTL8211F-CG, and this happens to be exactly the physical layer I ended up going with, because now we have a working reference design, at least from the schematic side of things. We can easily see how this physical layer needs to be connected up, and we have a suitable part that we could use in our design. Now, keep in mind, always make sure that you've checked that the manufacturer lifecycle, if you can even get this part from vendors and distributors, and if this part is suitable for your specific needs. Just because it's an Ethernet physical layer, which happens to be able to interface with your specific Mac and your processor, doesn't mean it'll work for your specific situation. So really double check that. But in my case, I needed just a generic Gigabit Ethernet capable PHY, and this is the one I then went with because it also gave me a nice reference to compare my schematic to. Before we move over to the schematic, let's go through the datasheet for this Realtek physical layer, just to familiarize ourselves with the typical structure of a PHY datasheet and see what sections we need to pay attention to when designing hardware for something like this. As usual with datasheets, we have the general description, block diagram, pin assignments, which we'll need for creating the schematic symbol, then we have to pin descriptions, function descriptions, and more. So let's go through a couple of these sections just to familiarize ourselves with this. I typically don't like just simply copying schematic diagrams without understanding them, and we might have different configuration requirements. We might want to use different setups, so it really pays off to go through the datasheet even if you have maybe a suitable reference schematic available to you. In terms of configuration of this file via the MDIO interface, they also list the register descriptions, which will be useful when you're doing your firmware bring up. In terms of the features for this physical layer and why it might be suitable for this design is that it supports 1000 base T, it's also download compatible to 100 base TX and 10 base T, and for our needs supports RGMII, which is perfect for our Mac we're using in this design. The nice thing is with this particular RGMII interface, it supports various different signaling standards. So typically it might be 3.3 volts or 1.8 volts. In our case, we'll actually be using 1.8 volts due to the AMD Xilinx Zinc. It requires an external 25 MHz crystal oscillator, but can also provide an external 125 MHz clock source, which might be great for driving the FPGA part as the clock input. It also provides interfaces for 3 LEDs to indicate, for example, link status, network status, speed, and it comes in a 40-pin QFN package. Now, I'm not a fan of laying out and routing QFN packages, but this is fairly standard for this type of part. A familiar diagram by now, here's the application diagram. We have our Mac interfacing via MDC and MDIO, and the RGMI interface to this physical layer, then via magnetics and a connector, or again, just using a MagJack. In addition, here we can see it needs probably a few different power supplies. It needs an external crystal oscillator, and it can also drive some LEDs, which are typically integrated into the RJ45 connector as well. As we scroll down the datasheet, of course, we'll expose more information and in more detail, for example, what pins there might be on the physical layer and what externals we might be needing. Then, of course, the pinout, which would move over to our ECAD program, as well as pin descriptions, which are very, very important. And I'd strongly suggest taking your time and going through these to see what pins there are for this particular PHY. What's typically also very critical with physical layers is that many of the pins are multi-purpose. For example, some of the RGMII interface pins also double as, on power up, for example, as strapping option pins. So we can see that in section 7.8 of the datasheet, hardware configuration. On the left-hand side, we have the specific pin, for example, RxD3, RxCTL, RxD2, and so on, all form part of one set of the RGMII interface, but they also serve a different purpose. On the right-hand side, for example, the physical layer address, if we have certain delays on the TX or RX buses, and configuration, for example, of the internal LDOs. So we can't just blindly hook up the RGMII interface. A lot of times with these physical layers, we have, again, multifunction pins, which we can configure via strapping, so adding external pull-up or pull-down resistors. This is detailed in the datasheet, of course. For example, the PHY address pins, if we want to turn on or off the PLL, if we want to add delays, we need to add certain value resistors, high or low, to these pins as indicated here. So again, you can't just simply blindly copy a reference schematic. It depends on the situation, on your voltages you're using, and your configuration of your physical layer, that you do have to probably make some adjustments to your schematic. We've just skimmed the datasheet very, very quickly, not all of it, of course. So make sure to take your time checking out which physical layer is suitable, then checking out the datasheet. And now let's move over to the schematic in Altium Designer. Before we jump over to the physical layer, let's just look at the processor side where the Mac is interfacing through various I/O pins. And for this AMD Xilinx Zynq XCZ020, this is in the PS bank mapped to these various pins. So for example, pins 16 through to 27 form part of the RGMII interface. We have the TX clock, then we have this 4-bit wide TX bus, TX control, then we have the same thing for the RGMII RX. Specifically, also at the bottom, we have Ethernet MDC and Ethernet MDIO, which form part of the management data interface, which is to set up the physical layer, various registers, and configure it to whatever application we need in software. On a free I/O pin, I also have an Ethernet reset signal, and this can be mapped freely just to do a hard reset of the physical layer. We won't be going to pinout or how we came up with this pinout in this video. If you're interested in seeing how the pinout is selected for this particular AMD Xilinx Zynq chip, again, please check out video number 99 on my channel, which goes through the Vivado design and sees how we even came up with this pinout. What's important for us, however, is that for this particular processor, and again, it depends on the processor you're using, if you want to use Ethernet for this design, we need to run the I/O voltage at 1.8 volts. So for this PS bank, for these RGMII signals, these are at a signaling level of 1.8 volts. And as we can see in the power supply section here, MIO1, which is the bank for the processing system I/O pins, it's connected to 1.8 volt supply for the processor, which integrates the Mac. And this we need to keep in mind for setting up the physical layer. So jumping over to the physical layer, this is the part we have seen previously and the datasheet. So let's just zoom on that part to start with. On the top hand side, we have our power supply inputs, outputs, decoupling. At the bottom, we have our ground connection. Because this is a QFN IC, typically the QFNs will have the exposed pad in the center tied to ground. And this is for electrical and thermal properties and reasons. This particular physical layer requires various different I/O or supply voltages. In particular, we need a digital 3.3 volts with some decoupling, which is tied to 3.3 volts generated from an external buck converter. We have DVDD RG, and let's jump over to the datasheet. This is the RGMII I/O pad power. So in a certain configuration mode, this needs to be tied to the I/O voltage level for the RGMII signaling. And that's why here, pin 28 is tied to 1.8 volts and also decoupled with a 100 nanofarad cap to ground. We also have a VDD33, and the A in the name signals this might be an analog interface, and this is to drive the analog signals on the right-hand side of the PHY, which we'll get to in just a second. And that needs to be connected to 3.3 volts, but also filtered beforehand, typically with a PI filter. Now, I know farad beads are a controversial topic, but anytime I have an analog supply, I at least like to put a placeholder series element, even if it's just a 0 ohm resistor, that in case I do need to filter or I do need to add a bead for whatever reasons that might be, for EMI reasons, for example, I can add a place in there rather than having a straight connection, for example, directly to my power planes. So for the AVDD connections, I have this filter structure feeding into both of these AVDD pins. Then we also have these 1.0 volt pins, for example, DVDD 1.0 and AVDD 1.0. And these are actually internally generated by a switching regulator internal to the physical layer, and that's pin 30. Pin 30 is the switch node of the internal regulator or the LDO regulator. Then we attach a typical LC filter. And this is according to the datasheet and various reference designs, the inductor and capacitor values. But that then generates the 1.0 volts for DVDD 1.0 and AVDD 1.0. Of course, if you already have 1.0 volts supply in your system, you could be using that, or you could choose a separate part that doesn't need a 1.0 volt supply. In any case, the actual supply voltages and filtering configurations will depend on the particular physical layer you're using. There could be physical layers which need more supply voltages, which have their own LDOs or regulators internally. This is particular to this particular physical layer, so make sure you check that out on the datasheet. Now moving on to hopefully something more interesting, we have the left and right sides of this physical layer. This is segmented that on the left hand side we pretty much have all of the MAC connections as well as some clocking, and on the right hand side we have our analog and LED sides. Let's start off with the left hand side. Some signals we should be familiar with by now are the RGMII signals. That's the RX side, 4-bit wide data bus control and clock from the PHY to the MAC. Then we have the TX side, which is from the MAC to the PHY, again 4 bits wide data control and clock. Before we get to the strapping options, for these RGMII signals, I'd strongly suggest on each line adding a low value series termination resistor, or at least a placeholder. In my case, because I had 22 ohm resistors in my design, and this is typically a pretty good starting value, I added on each of the RGMII lines a 22 ohm resistor. And we'll see later on the layout how these need to be placed. I have them on the RX lines, but I also have them on the TX lines. And they're placed on the schematic to be close to the transmitting side because that's how they will be placed later on the PCB side. This is series or source termination. We want these series resistors to be as close as possible to the driver side. And these will help or can help with signal integrity to reduce reflections and ringing, which improves the overall signal integrity and EMI signature. I typically start with a low value resistor, and then on the real world PCB, I'll look at the rising and falling edges to see if there's any overshoot, undershoot, excessive ringing, and then we can increase or decrease the value of those resistors. But it's better to have them in place straight away in the design because you might have to respin your board otherwise if you do see ringing on these traces, whereas here we have them directly in place. Of course, you could use resistor arrays. I typically use single resistors so I can change out individual resistors on their own rather than having to replace a whole resistor array. What you've probably already noticed is other than these series resistors is that I have these pull up and pull down resistors on certain pins, including pins of the RGMII interface. And as we saw previously on the datasheet, this is because of the hardware configuration and that some of these pins double as strapping pins. For example, IXD3 controls the least significant bit of the physical layer address. So therefore, if you look at PHY IXD3, in the schematic symbol, we have a /PHY add 0, which indicates this is a strapping pin that needs to be configured. So let's look at this signal. That goes to a pull-up resistor to the I/O voltage of our RGMII interface. So at startup, this line will be pulled high by that resistor, and therefore the least significant bit of this address will be a 1 in this particular case, or whatever the datasheet says it is for that state. And this of course needs to be configured for each one of these strapping options. For RX delay, TX delay, PLL off, and so on, you need to choose the right configuration of strapping options, that is pull down or pull up resistors, depending on your requirements. And this depends on your system requirements, on what your MAC requirements are, your addresses, if you have multiple PHYs, and so on. Keep in mind this Altium view, if I click on the bottom left hand side, I do actually have variants, so that's why it might look a bit odd that all of these resistors are populated, some of them actually aren't. But also the placement is important of these strapping options. Now we could place these strapping options very simply, for example, on the left hand side of these series resistors. But keep in mind these are series termination resistors, so they will be placed close to the driver. The driver for these RX lines are from the PHY to the MAC. So we're going from the right to the left to the MAC, very simply speaking. If we moved these strapping resistors to the left-hand side, this would form a potential divider. So we'd have a slight bit of signal attenuation due to the series resistor and then those strapping options. Now, typically that isn't too much of a problem, but it also means that we have a somewhat high impedance load directly after the series termination resistor, so the preferred configuration is something like this. So strapping resistor before the series termination, then off to the load. The values are listed in the datasheet. For example, for the pull-ups, they wanted 4.7 kilo ohms. So I chose something I had in my design anyway, in the same ballpark, about 5.1 kilo ohms. But keep in mind, there might be some more stringent requirements, and they might be different for pull-up versus pull-down. So that was pretty much the RGMII interface. You'll see I also added some net directors around this just to give these a net class name, because we will have to delay tune these nets later on in the PCB design within the RX and TX groups. So that's why I like to add a constraint, for example, a delay matching constraint, and give them a net class name. But that's pretty much all there is for the RGMII configuration. It's essentially just a point-to-point interface with series termination and some strapping options depending on the physical layer of your design. Then we have the MDIO interface, which is our management data interface. We have the IO line and the clock line. Very similar to I2C, except we have different requirements on the pull-ups. We need a pull-up on the MDIO line, but not on the MDC line. And these are pulled up also to 1.8 volts. We also have an interrupt, which does require an external pull-up, and we have a reset signal, which also goes to the MAC. So these are for configuration and reset. Again, details are listed in the datasheet, but these are typical signals you will find pretty much in any physical layer. In terms of clocking, we have two pins. We have a pin 36 and 37, which are crystal in and crystal out, or external clock. So either across these two pins, 36 and 37, you can connect a crystal, so without an oscillator, because they actually have a driver internally in the PHY. But in my case, I prefer to typically use an external oscillator, which in this case for RGMII needs to be at 25 megahertz. Again, series or source termination, feeding into the external clock input. And according to the datasheet, pin 36 needs to be tied low if I'm using an external oscillator and not using the internal one with an external crystal. As we saw initially, very quickly on the datasheet, there's also a clock out pin, which is actually a 125 megahertz clock frequency clock that we can use to feed other devices. And I actually use this, again with series termination, to feed the programmable logic section of my FPGA. So rather than needing an additional crystal or additional oscillator, I can simply take this clock output. Of course, this isn't required and depends on your situation. But hopefully this showed there's actually not too much to it. Again, it's follow datasheets, it's follow recommended guidelines, and follow the schematics from, for example, reference designs. So just reminding ourselves from the block diagram, we've now looked at the left-hand side, the interface between a system on chip and the Gigabit Ethernet PHY with RGMII signals and MDIO. Now we're moving to the right-hand side with our MDI connections to the RJ45 connector, and in our case, with integrated magnetics. For Gigabit Ethernet, and for this particular physical layer, this connection is very, very straightforward. It's even simpler than the RGMII connection. We have a set of 4 differential pairs that simply go from the analog side of the physical layer to the RJ45 connector. If we had external magnetics, there would be an additional element in the center here. We might need some termination, some more decoupling. We might need some external peripheral components. But if you use a MagJack connector, not just from the schematic, but also from the PCB design, it makes things so much easier. So that's where I like to choose MagJack connectors, so RJ45 connectors with integrated magnetics. And it's simply a point-to-point connection for differential pairs. I've indicated that with the differential pair net directive, as well as I've added again a net class for these MDIO diff pairs. The RJ45 connector itself, this particular one here, is quite cool. It has integrated LEDs, so a green one and a yellow one, and integrated capacitors for the shield to system ground connection. Jumping over to the connector datasheet and looking at the guts of the connector, we can see it has the integrated transformers as well as termination, which we otherwise need to have externally. If we don't use a MagJack connector, we have the 4 differential pair connections, and as well the termination feeds off to a high voltage, low value capacitor, this 1 nanofarad capacitor, to pin 10. Because we have this integrated high voltage capacitor, we can tie pretty much directly to system ground. So depending on what enclosure I'm using, how I'm doing my shielding or grounding, you can have different options. Here, I'm simply tying that pin 10 directly to my system ground. The LEDs themselves, we have the anodes and cathodes. The anodes are tied to the 3.3 volts, and the cathodes are tied to the LED driver pins of the physical layer. We have 3 LEDs, and we can look at the datasheet what they mean. They tell us the speed or link status, but also, again, because of this /, they double as strapping pins. So they set, for example, LDO voltages, what the external supply voltages are, and so on. so therefore you will also need pull-up and pull-down resistors. The datasheet again tells you how to hook these up, depending if you want logic high or logic low activation of your LEDs. You have to attach these resistors slightly differently depending on the configuration, but again, check out the physical layer datasheet for exact implementation information. Lastly is this RSet pin, pin 39, which is simply a bias resistor to ground, which needs to be a pretty precise 2.49 kilo ohm resistor, 1% tolerance. And that's again given in the datasheet. So overall, pretty straightforward. We have power and ground, various supplies as listed in the datasheet, RGMII connection with series termination, our strapping resistors, MDIO interface, 25 MHz crystal or crystal oscillator. On the right hand side are MDI connections, simply to a MagJack of our choice, LED configuration, bias resistor, and that's about it. So now we can move over to the PCB design aspects. Before we jump over to the ECAD tool to look over some PCB design guidelines, I will also leave some more links in the description box below that link to application notes and videos that go into a bit more detail on specific topics. For example, this application note by Pulse, they have layout considerations for Ethernet magnetics and MagJack connectors. So depending on if you're using external magnetics, as is shown in this image in the center here, versus MagJack connectors, there are of course differences in layout and routing. Then application notes, for example, by Texas Instruments are always great on general Ethernet PHY PCB design layout, including a checklist. Zach Peterson also has some articles which I'll link, as well as a video on grounding in Ethernet with and without MagJacks, which goes into more detail on that specific topic. Rick Hartley, as usual, also has great videos, and one in particular with Robert Ferenek, Ground in PCB Layout. Although it's only a small part of the video, Rick Hartley briefly touches on shielding and grounding for RJ45 connectors. Again, links to this will be in the description box below. For our specific case, and as is the case for many designs, we will be using, or we have been using, a MagJack connector which integrates the magnetics, which makes our PCB design and layout far simpler and a bit less stringent than if we were using external magnetics. To get some ideas, we can also look at other boards, how other people have successfully implemented MagJack connectors and Gigabit Ethernet PHYs, for example the RTZ7, where we looked at briefly the schematic earlier. We have the physical layer, where my cursor is on the left hand side, very close to the MagJack connector, and the MAC, which is integrated in the Zinc system on chip, is on the right hand side, so you can get a sense of scale and placement and how typically want to place these parts. But now let's jump over to Altium Designer and let's go through some PCB design tips and aspects, how I implemented this successfully in my own designs. Here we have this A-scope PCB. We have the system on chip on the left-hand side, which integrates the Gigabit Ethernet MAC. We have the PHY highlighted now in the center, and right above that, we have the RJ45 connector with integrated magnetics, this MagJack. This PCB itself is an 8-layer PCB. It's separated into a digital section at the top and an analog section at the bottom. And this is actually a fully isolated design between digital and analog sections. Of course, now we're just going to be focusing on the Gigabit Ethernet section of this design. So let's firstly explore the stack-up. This is an impedance control PCB, and I did talk to my manufacturer, in this case PCBWay, to get suggestions and recommendations on the specific stack-up for my requirements and for my impedance control requirements, and then also calculations for what trace widths I need to meet certain impedance specification. Before we move over to impedance control, the stack-up is an 8-layer board. Again, we have signal, ground, power, signal, ground, signal, ground, signal. So adjacent to every signal or power layer, we have a dedicated ground layer. So that means 3 of my 8 layers are entirely dedicated to ground. My main routing for these Ethernet signals will be on layer 1 because most of my componentry is on layer 1, and this is a microstrip with a ground reference right below, but I will also be using layer 6 to do the majority of my RGMII routing as a strip line because we have shielding above with layer 5 ground and below as layer 7 ground. So we have microstrip at the top, layer 1, and strip line layer 6. Again, ground adjacent to every signal layer. We have specific requirements on the thicknesses of these dielectrics and the dielectric constants, and again, this stack-up is from PCBWay after talking to their sales reps to see what can meet my specifications. In terms of impedance control, if I switch over to the impedance control tab, I have various different impedances in this design. One is single-ended 50 ohms, and single-ended 50 ohms will be needed for all of the RGMII signals, and I'll generally route all of my, for example, clock signals or even my control signals with 50 ohm controlled impedance. So therefore, for my strip line signal layer 1, that width to give me a 50 ohm impedance is 0.12 millimeters, and this was confirmed with PCBWay. Then for strip line signals, that's be on layer 6 predominantly, I need to go down to a 0.1 millimeter trace width to hit that 50 ohm impedance. Again, for the RGMII signals predominantly. We also do have these MDI signals on the right-hand side between the physical layer and the MagJack, and these need to be routed as 100 ohm differential impedance pairs. So jumping over to Impedance tab again, click on diff 100. These are the impedance specifications I got from PCBWay. So we have a trace width of 0.1 millimeters and a trace gap of 0.25 millimeters, give me an impedance nominally of 100 ohms. That's for my microstrip layer 1, and for strip line layer 6, I have 0.1 millimeter trace width and 0.3 millimeter trace width to give me about 100 ohms differential impedance, with a single end impedance about 45-50 ohms. So keep in mind, for RGMII, for Gigabit Ethernet, you will need controlled impedance traces in pretty much all cases. So speak to your manufacturer, get yourself a decent stack up, remember ground adjacent to every signal layer and every power layer. And the reason these trace widths are so narrow is because the dielectrics are thin and I need 50 ohms and 100 ohms differential, which drive down these trace widths, because I'm also fanning out a BGA package and I do need very narrow trace widths to get past the via grid and the ball pad grids as well. So that's why these trace widths are rather narrow to hit these impedance specifications. But with this stack up in mind, knowing that we'll be routing predominantly on layer 1 and layer 6 as controlled impedance, 50 ohm single-ended, 100 ohm differential lines, we can get started looking at the layout and routing. Again, my Mac is on the left-hand side, physical layer in the center, and RJ45 connector at the right at the top above the physical layer. Because we're using a MagJack, again, this makes the PCB design a bit simpler. If we're using external magnetics, if we have further isolation requirements, we typically might want to increase the distance between the RJ45 connector magnetics to the physical layer. So you can see here the PHY and MagJack are rather close together. In this case, I didn't have any particular requirements, so that's why I kept them fairly close. I do, however, also want to keep my distance between my Mac, which is integrated into this processor, and the physical layer close as well. So the RGMII signals across this horizontal here should be kept as short as they can be within reason. So I wouldn't, for example, want to place my Mac on the far left-hand side and the PHY on the far right-hand side. You want to place them sensibly close. So in my case, the signals need to travel an optimal distance, let's say about 30 millimeters, just a bit above an inch. So even from the layout, before you start routing, you want to try and arrange your components sensibly. That means, for example, for the physical layer, looking at where the various pinouts are. At the top, we have the MDI connections, so it makes sense to place the RJ45 connector in that direction. On the left-hand side and on the bottom side, we have the RGMII connections, so it makes sense that they stream then off to the Mac or to and from the Mac. So again, as usual, these are typical PCB design guidelines. If you do a sensible layout, you'll have a much easier time of routing this board out as well. Let's start off with the simplest part first, and that is the Mac, which is integrated into the system on chip. This is this BGA style package. This is a 0.8mm pitch BGA, so I do dog bone routing. The RGMII signals, or generally the Ethernet signals, are color-coded with these shades of green. For example, in RxD1, we have the pad here, short trace dog bone routing to a via, and then I drop down from layer 1 into layer 6. Normally, my trace widths for these controlled impedance traces are, of course, set to a 50 ohm controlled impedance, which is a width of 0.12 millimeters. It depends on whatever stack up and impedances you require in your design. So from a pad into the via, drop down to layer 6. Layer 6 I chose again because it's a strip line. I have ground on layer 5 and ground on layer 7, but also rather than dropping from layer 1, for example, to layer 3, I drop from 1 to 6 because of my via, I only have a stub on layer 7 and layer 8. So a comparatively rather short stub compared to routing from layer 1 to layer 3, which leaves a much longer stub through the remaining layers. So I've tried to fan out as best I can. Of course, the Ethernet signals aren't the only thing in this design. I do have DDR memory, USB high speed, and so on. So this needs to fit somehow into this design. But all these color-coded green signals are my RGMII signals. So this is typical dog bone routing, but controlled impedance, trying to minimize the stubs. Now, unfortunately, because of the constraints of this board, and because I have a lot of vias on the bottom side, loads of decoupling capacitors and other components, for the driving side, for the TX signals, which come from my Mac and go to the PHY, I can't really place my termination resistors particularly close. So this isn't particularly optimal. Ideally, your termination resistor should be as close as possible to the source side, but we will see that for the RX side and the RGMII signals. The RGMII signals for the Ethernet PHY, going from the PHY to the Mac, are these RX signals from the QFN package on the bottom side. And these route out with short controlled impedance traces through the strapping resistors, which we saw in the design, which set various PHY config options, route through the strapping resistors first, then into the series termination as we saw in the schematic. So we have short traces directly into the pull-up or pull-down resistors directly into the series termination. So this is a far more ideal placement of the termination resistors. They're placed very close to the source because this is source termination, through the strapping resistors, not leaving much stub, straight into the termination resistor, into the via, and then we dig down into layer 6 again, and we do the connections between the MAC and PHY. So again, controlled impedance based on the calculations provided by your manufacturer, source termination resistors close, but we route through the strapping resistor first into the source termination resistor and then into a strip line configuration if you're using a strip line configuration. Also, anytime I can, I of course try to keep space between my traces. So rather than routing, for example, signals like so, really close together, I try to spread out my signals and my traces fairly evenly to minimize crosstalk. Also, anytime I do a layer transition, for example, from layer 1, which has a reference at layer 2, to, for example, layer 6, which is reference layer 5, reference layer 7, I try to place transfer vias. So a grounded via that aids in the Z-axis transition when I'm switching reference planes. So this stitching via also serves as a transfer via for RxD3. Now, sometimes, of course, because there are signals on other layers, you might have to place your stitching and transfer vias a bit further away. But in generally, if you can, place one transfer via close to these fairly high-speed signal vias. Other than series termination, crosstalk issues, controlled impedance, we also need to take care of the delay matching between the signals. So we want to make sure that within the groups, for example, this dark green group, which are the TX signals, we want to delay match those signals within that group. So within TX, we want to delay match, and within RX, we want to delay match. So depending on what ECAD tool you're using, for example, in Altium Designer, I can set up net classes and look at, for example, the TX groups, and I can see, I can either do these as X signals or as not, where I can combine them with the series termination resistors. But you can see the trace lengths before the series termination resistors are matched. So these are all about 30 picoseconds in time delay, and also after the series termination resistors, these are delay matched, that they're all about 360 picoseconds in delay per line. And that's why I have these meanders and these squiggles within this group to match the delays within the TX and RX lines of the RGMII groupings. These meanders also, of course, need to be suitably spaced. You don't want to place them too close together within themselves and also between other signal lines. Again, this is for crosstalk reasons. And of course, you don't have to match them to within 0 picoseconds. There is, of course, some skew allowable, so 50, 100 picoseconds or even more is completely fine. I tend to think why not match them as best as you can. As we can see here, these are matched pretty much all to each other. But keep in mind, you also need to include package delays in these calculations. And Altium Design actually takes care of this for you, but of course you can just use a spreadsheet or manual calculation or whatever ECAD tool you are using. If I click, for example, on my Mac on one of these pins, you can see every net also has its own propagation delay, which is due to the package delay of the particular component that I'm using. In this case, this is Zinc System on Chip. I can extract the package delays from Vivado, but this depends on what processor you're using. So these need to be taken into account along with the actual trace delays themselves. So therefore, RGMII, controlled impedance, crosstalk, spacing, transfer vias, delay matching, and you're pretty much golden if you follow those rules. The MDI signals are right at the top because of the placement of the PHY to the MagJack connector. These traces I try to keep as short as possible. Now these are 100 ohm differential controlled impedance differential pairs. Therefore we have a specific spacing and we have a specific line width to maintain 100 ohm differential. Now of course maybe this routing isn't entirely optimal. One, because of the pin out of the connector. So this is a rather funky pin out. Pin 4 is the positive part of line 1 and pin 7 is the positive line of part 1. So that's why you have to have this funky connection here. But also, because we're routing straight from the top layer into these through-hole pins of this MagJack connector, there is actually a long stub all the way through the board. Now, of course, you could trim the connector pins, or you could place the connector on the opposite side, or the PHY on the opposite side, or you could route out of the physical layer, drop 4 differential pair vias, route on the bottom layer, and then into the connector to have no stub left over. But for this design, and even for Gigabit Ethernet speeds, this is still okay routing like so, and it just makes the routing far easier because I can simply route out of the physical layer, diff pairs into the through-hole pins of this RJ45 connector. And as you can see here, because the magnetics are integrated into the connector, it is so simple to route into this. We don't have to do anything special other than short controlled impedance pairs, and you can see I've added some teardrops to aid reliability when soldering. Lastly, just in terms of the chassis or shield connection, because I'm not using a metallic enclosure or any particular enclosure in this case, I'm simply tying pin 10 where the MagJack integrated a high voltage capacitor directly to my system ground, but I also have options for the other chassis ground or shield ground connections to go through a high value cap here or simply through a 0 ohm resistor to my system ground. The grounding itself again depends on the system you're working with, and please refer to the videos and the links I mentioned previously, which will be in the description box below. Just to briefly cover all the bases, of course, for this QFN style package, because we are fanning out most of these pins, having decoupling capacitors placed right around this package on the first layer might be a bit difficult because of all the signals we have. So actually what I did and what I like to do oftentimes is if I do double-sided assembly is place my decoupling capacitors on the bottom side. So the way I do this is I have, of course, my exposed pad. I have the grounding vias internally. This is both for electrical and thermal reasons. These are my ground return vias. And anytime I have a power pad on the outside perimeter, I neck down into the width of that pad, place a via close as I can, given the other signals that need to route out and into this package, place my decoupling capacitor on the bottom side, connect with a short wide trace, and then a ground flood that connects to the grounding vias that can go back up into the QFN package. Now, although this is not optimal from a decoupling standpoint, it makes my life a lot easier fanning out all these signals, and I think it's quite a neat little trick, and this seems to have worked well on many designs with QFN packages, even these high-speed Gigabit Ethernet physical layers. So I try to keep short wide traces, dig down to the via to the bottom side, place my decoupling capacitors so the ground pads face towards the exposed pad vias, and so I have my current loops like so. Other peripheral components, such as the bias resistor, I also try to place close to the device because these are fairly important, as well as, for example, the crystal CMOS oscillator that's driving the 25 MHz clock on pin 37. I try to keep that close to the physical layer itself. But overall, there's not too much to the PCB design other than keeping controlled impedance, placing your series termination resistors as close as you can to the relevant driver outputs, keeping reference grounds close, adding transition and transfer vias, and if you can, using MagJack connectors because that makes your life quite a bit easier. There are, of course, many other guides that go into slightly more detail on various topics, in particular if you're using external magnetics, but as usual, the basic PCB design guidelines apply, which always do. Keep decoupling capacitors close as you can, keep traces and features away from each other if you can, keep traces short, use controlled impedance, use stitching and transfer vias, place ground vias close to relevant ground pads, do not cross ground or power plane splits, always maintain a solid reference, and so on and so forth. The usual high-speed PCB design guidelines apply, but we do have to consider series termination, controlled impedance, and the other topics we talked about. Thank you very much for watching this video. I hope it was useful, and I hope it served as somewhat of a primer to get you started on your own Gigabit Ethernet PCB designs. They might seem a bit daunting at first, but then again, once you follow the very basic simple rules, you should be fine with your design as long as you adhere to them. If you haven't already, make sure to like the video, leave a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest PCB design, hardware design, and embedded systems videos. Thanks again for watching, and I hope to see you in the next one. Bye-bye.